Hey there, TouchDesigner developers, DiLaura here with the Interactive and Immersive HQ. In this video, we're going to have a look at TouchDesigner's new series of DMX-related POPs. We'll have a look at how things used to function in TouchDesigner in terms of sending DMX data before the introduction of POPs, and then dive into the new operators and look at the great improvements that they have made in terms of the DMX workflow. I've based this example around my particular setup. I've got an ESP32 running WLED connected to a small 8x8 LED matrix. I'm sending the data to it using this network here, and you can see this same animation appearing here in this little cell phone video that I took of it. So this example, of course, could be adapted to any type of fixture that you have available, but this one provided a really simple opportunity to showcase how these operators work. So I thought that I would start by looking at the way that we used to send DMX data prior to the introduction of POPs. I also want to mention that this is still a totally viable way of sending DMX data from TouchDesigner. It's just going to be, of course, a little bit of a different setup than the POPs variety that we'll cover later in this video. So prior to the introduction of POPs, the only way that you could send DMX data in TouchDesigner was via the DMX Out CHOP. And what that meant is that no matter where your data started, whether that was in a texture or maybe in some CHOP channels or even in a SOP, if you so chose, it would then have to be converted into CHOP data in order to be correctly sent. And so one of the very typical methods that you would see for sending DMX is that you would start with a texture of some variety and then convert that data into CHOP channels. Using a texture as the starting point is often your best bet because, of course, it allows you to visualize the content that you're going to be sending to those fixtures. It's a little bit easier for us to understand the colors and the aesthetic of the visual that we're creating over here in our ramp top than looking at the same data in this kind of graph form in our top to CHOP. So we're going to do a quick rundown of how this network works from a high level, just so you have the understanding, if you run into one of these networks in the future, how things are working. So we start off with our texture, as I mentioned, the ramp top. And in this particular method, it's very important that the texture that we use generates the correct amount of data. So I have, as we saw at the beginning of the video, an 8x8 LED matrix. And so that means that I want to generate a texture that's generating the correct amount of data for that matrix, meaning that my resolution should be 8x8. If I were to generate something larger than that, then we would essentially be creating excess data, which would not be utilized by the device. And we also wouldn't see the texture correctly mapped to the matrix. So anyway, I've set that resolution based on my physical fixture. And then we over here convert that data from a texture into CHOP channels so that we can eventually send that via the DMX Out CHOP. So I've gone ahead and removed the alpha channel here because we don't need that for this application. And then I've also output the channels as a single channel set, meaning all of the red values for all of the pixels in this texture are in a single channel, likewise for the green and the blue. And down here, just to kind of explain what's going on here visually, I've created two different illustrations of what this data looks like. So essentially, every sample in this top to CHOP is going to contain values red, green, and blue for each pixel. So that is to say that, let's say for this upper left pixel, if we're calling that coordinate 0, 0, we would have the red, green, and blue values for that pixel split across 3 channels. So essentially each column is going to reference 1 pixel. Down here, we have that in table form. So again, the sample in our CHOP channel is going to count up from 0. And so each column is going to be associated with the RGB color values for each pixel in that texture. So that's fine. But Unfortunately, this is not the sort of formatting that is required for our DMX data. Now, just to give you a brief look at how that DMX data is set up, we have something called a universe, which contains up to 512 channels. And then we can have multiple universes of data. We can have more than just the two that I'm showing here to account for all of the channels of information that we need. And so each one of these channels, up to 512 per universe, can correspond to something like, say, the brightness of a light, or maybe the pan of a light or the tilt of a light. And when we are dealing with RGB lights, as we are in this particular example, we actually have to split that data across multiple channels. So our first LED in the matrix will, for example, use channels 1, 2, and 3, and that allows us to specify the red, green, and blue brightness values for that particular LED. So if we take it back to TouchDesigner, the way that our DMX Out CHOP is going to expect the data to be formatted is that each CHOP channel that is contained or sent out via this CHOP is going to contain a single universe's worth of data. So that means we can have 512 data points in that channel. And again, each channel will account for one universe. So as we just looked at, we're expecting essentially sequential data for this particular fixture of RGB values for each pixel, or rather LED, in this matrix. And so having that data split across 3 channels is not going to help us, because that would essentially be having a single universe for each color. We want those values to be sequentially ordered in a single channel instead. And so that is exactly what our shuffle CHOP here is doing. We're sequencing those samples so that, again, they become sequential in this final form in a single channel. Next up, we have a math CHOP, which is used to increase the range of those values. So you'll notice that back here, well, really starting at our top 2 and then as well in our shuffle, our values in this y-axis of the graph are between 0 and 1. And that is because in TouchDesigner, color values are going to be defined in a normalized 0 to 1 range. For DMX data, however, we need to take this range and increase it so that instead of 0 to 1, we have 0 to 255. And so our math CHOP is being used here to increase that range accordingly. So here in the DMX Out CHOP is where we actually send that data out to the fixture. And we can choose our various network settings, like our IP address, whether or not we want to multicast the DMX data, and various other controls as well. We can also choose the particular interface type that we want to use. That can be like a physical hardware device, like a NTEC USB device. It could be sent over serial, or we can use these various network protocols like ArtNet or SACN. I've also gone ahead and set the format here to packet per channel, which is going to treat each sample in this CHOP channel as a DMX channel. The other option we have here is to set up packet per sample, which is going to assume that each CHOP channel corresponds to a DMX channel. So there are 2 ways to set that up, but this one, at least for this particular scenario, was the simplest. Then at the bottom, I've got my routing table, which is where I actually choose what CHOP channel is routed to what particular net, subnet, and universe. Assuming that we've set everything up correctly and that my computer is connected to the internet as well as my ESP32, I should then be able to send that data and receive it on the device and see it on the matrix. So that was a quick look at how DMX data was sent in TouchDesigner up until the introduction of POPs. Now we'll shift gears and look at sending DMX data with the new DMX POPs. Let's begin by looking at some op snippets that showcase how DMX functions in the POP family. In this first example, we're creating and sending some content to an LED strip. So the way that DMX works in the POP family is that we are going to use per point or per primitive attributes, send those to a DMX Fixture POP, which we can see over here on the right, And that is what we'll use to actually convert all of those attributes into a DMX channel layout and thus DMX data, which we'll send out using the DMX Out POP. So rather than having to worry about creating numerous DMX channels depending on, the type of fixture that we're working with, the DMX Fixture POP is going to do all of that for us. It'll loop through all of the points and primitives in the content or the pops that are connected to it and automatically create all the channels that we need. So for this particular example, we have a line pop representing our LED strip. Each one of the points on this line pop have a color attribute assigned to them here in this lookup texture. So we've got R, G, and B values for each point in that line primitive. Over here in the DMX Fixture POP, we merely have to point this operator to the attribute that we want to use, and it will automatically go through, create the DMX channels that we need, and we don't even have to worry about scaling up the data from that 0 to 1 color range to the output range of 0 to 255. So in this case, we have a really simple fixture, but it's taking care of a lot of setup that we previously would have had to do manually when working with the DMX Out CHOP. Let's take a look at one more example to see what we would do in the situation where we don't have something like, a typical LED strip and maybe have a moving headlight instead, which has many more control channels rather than just simple RGB values for each light. So in this case, we've got a single moving headlight, which has a wide range of DMX controllable features. What we do is to add a number of custom attributes to represent those controls. We can choose to add, let's say, if we've got an XY position as one of the possible channels of control, we can set up the number of components for that value as well. And then on the points page here, we could set the, let's say, static or default values for any one of those attributes. The DMX Fixture POP will take care of, again, doing all of that channel layout for us, so we don't have to then go in manually and work through that. But the main point here is that we're using a different type of geometry, a single point to represent this particular fixture, and we're adding all of these custom attributes to be able to control the various DMX controllable features of that fixture. With that aside, we'll head back to our network and start building today's example. So what we're going to do is to, of course, have to choose our generator pop first. In this case, as we're dealing with a matrix of LEDs rather than a simple LED strip, we're going to use the grid pop. And like the example we saw for the LED strip, we'll be assigning color attributes to each one of the points within this grid to then be converted into DMX channels and sent out to our fixture. So I need to set my columns and rows to the correct value for this particular fixture. So I've got 8 rows and 8 columns. And another thing that I like to do, because this is not going to be a rendered piece of geometry like we might typically use pops for, we're dealing with it in a data sense. And thus we don't really need this quadrilaterals connectivity, and we can set this to the point primitive setting instead to give us a clearer view of the points that make up that geometry. So again, all I've done here is to set the connectivity to point primitives, my columns to 8 and my rows to 8. The next thing we're going to do is to add a normalize pop, which we'll put to the right. And we're not going to worry so much about what we're doing with this at the moment. We'll just push through and set this up in the correct way, and we'll come back and look at it in a moment. So all I'm going to do here is to set the output attribute scope to something different. I'm going to type in the word lookup as my output attribute scope, which will take this input attribute, which is the point position. It will normalize that. So that is to say, it will output it in a 0 to 1 range and sort of remap it into that range and store it into this new attribute called lookup. So I've gone ahead and hit enter there, and we'll follow that up with a lookup texture pop, which is what we're going to use again to pull in the color from the texture and assign it to each point within this grid. Of course, we're going to need a texture in order for this to function. So what I'm going to do is to head back to the top page and grab a ramp top. Now, in this scenario, we don't actually have to worry so much about the resolution of the ramp. We can choose to set it to 8x8 as we had done before, but actually the lookup texture pop will kind of take care of that interpolation for us. So what I'll do here is to set my colors, and then I'll work on some of the various settings for the ramp itself. Feel free to choose any colors you like. I chose for my example a blue to red gradient, but again, you can choose anything and even add additional keyframes if you want. So I've got red on one side, blue on the other. I'm going to set the type here to circular, and then I'm going to add an animation with this phase parameter by typing in ABS time.seconds and hit enter. Then I'm going to come down to this extend left setting. You'll see that there's kind of this harsh line as this animation kind of loops, and that is due to the extend settings here. And if I set that to mirror instead of repeat, you'll see we get a little bit of a smoother transition. The other thing I like to do is set the interpolate notches here to ease in, ease out, which will further smooth that transition from blue to red. That's all I've got to do in this operator. I'll then add a null, and this is the operator that will reference in our top parameter for our lookup texture. So I'm going to click on the lookup texture, drag null1 onto the top parameter. We'll see we now have a connection made between those two operators, but we don't see anything currently happening to our points. And that's because we need to set up an output attribute scope. We need to take the data that we are looking up and grabbing from this top and store it into an attribute. And so I can click the little drop down on the right. This is going to give me a handy list of attributes that I can assign this to. I'm going to choose color, and we'll then see that our points are now changing color. Now, before we move on, I'm going to adjust the viewer for this operator a little bit to make things a little bit easier for us to see. So I'm going to click the viewer active switch in the lower right. I'll mouse over the viewer and right click, and then I'm going to go to display attribute colors, and then keep mousing over that until you see color point under the cursor, and I'll click that, and you'll see that our points then sort of have expanded a little bit in their scale. So we're using a built-in visualization function of the new pop viewer, which allows us to visualize in color any attribute that is assigned to our points. And at the same time, it scales up the size of those points to make it a little bit easier to see. Another great thing that we can do here is to right click and go to display options, where we can then come to the pop overlays page and take this slider here called scale attribute overlays, and again increase that to make it even easier to see our color attribute for each point. So set that to whatever you like. Remember that this has nothing to do with the data that is contained within these points. Just like moving the viewer around inside of let's say a SOP, or even clicking and moving this viewer around has no impact on the data that is being generated by this operator. This is exactly the same. It's just a preview to help us understand what this contains. So I'm going to close that next and then deactivate the viewer. And now let's have a look. We may notice that our animation here looks different than what we see up top. And that has to do with our lookup index attributes. So we're using currently the point position, the X and the Y point position of every point in our piece of geometry here to pull in pixel values from this texture. Based on this parameter below, what we're actually expecting for that range of values that's provided by that attribute is something in a normalized 0 to 1 range. But our points currently are actually not in a normalized 0 to 1 range. They are in the x-axis, negative 0.5 to positive 0.5, and in the y-axis, negative 0.5 to positive 0.5 range. So essentially what's happening is, as this operator is looking for and pulling in data from the texture, it's expecting us to have coordinates in the 0 to 1 range, but we're giving it coordinates in the negative 0.5 to positive 0.5 range. So essentially, we're able to capture this lower left corner, and then anything 0 or less is going to push us beyond the boundaries of that texture. In that range beyond the boundaries of the texture, we actually have the ability to control how that is sort of interpreted, and that's done with the input extend mode parameter, and this will really help to visualize what's going on here. So if I change this input extend mode to 0, you'll see this upper right section where my X coordinates are 0 to 0.5, and likewise my Y coordinates are 0 to 0.5. That's able to correctly sample from this lower quadrant where, again, those coordinates when normalized would be 0 to 0.5. But anything where those either the X or Y coordinate values are negative, because we've set this extend mode to 0, those have turned to a black color. And so this is why we've gone ahead and normalized and created that new attribute in our previous step. If we choose from this little drop-down arrow on the right for our lookup index attribute U, lookup 0, and then likewise for the lookup index attribute V, lookup 1, we'll see that we then are able to correctly pull in and sample those color values from the correct position. Now, one thing that I do want to also mention at this stage is you might notice that the bottom row and the leftmost column are a little bit darker than the rest of the points. We have this interpolate function, which sometimes can be helpful for getting the color sampling to function correctly. If we simply turn that off in this scenario, we'll end up with the correct result. So that's how we can actually take the information from the texture and correctly map it onto those point attributes. So now we can move on and add the fixture pop, which, as we talked about earlier, is what we use to translate the attributes into actual DMX data. So I'm going to add that to my network. I'll connect the lookup texture pop to the DMX fixture pop. We'll see that we have a little warning right now that's saying we currently don't have any channels assigned, and so we're not sort of generating any DMX data. What we have to do is to head to the DMX profile page of this operator, and here is where we can actually choose the particular attributes that we want to take and convert into DMX data to be sent out to the fixture. So in this case, we only have this single attribute called color, which we want to send out as data. But if you, again, had something like a moving headlight, like we looked at earlier, you could add a large number of channels here and then pull in the corresponding attributes. Again, we only need the one for this particular scenario. So I'm going to type in for the name color. Next up, we have to use the attribute parameter to specify which attribute we want to convert into DMX channels. So I'm going to click the little drop down on the right and caution us, because you may think, okay, I'm just going to choose the color attribute because that is the data that I want to send out. The color attribute by default is going to be a 4-component attribute, meaning that we have the ability to store R, G, B, and alpha data into that attribute. And thus, if you were to just choose this color attribute and send that out to your device, what you would see on the device would not look like this animation we see here. We would have some extra data added in, so it would not be appearing correctly on that LED matrix. So we have some choices here as to how we deal with this. We can use swizzling, which you may be familiar with from GLSL code, where we can type in a period and then RGB to grab the red, green, and blue components of that color attribute. That would work. Or we could instead access those components independently, like we've seen before, where we add parentheses at the end and we could do color 0, color 1, color 2. And that would also function as well. So either of those options will work, but make sure that you make that distinction now, because it will save you from having to troubleshoot later on. You'll notice here that we have the value is normalized switch, which is one of those handy little helper tools where now we can provide normalized data to this operator and have the operator take care of that scaling from 0 to 255 that we used to have to do ourselves in the CHOP family. We also have the ability to choose what type of attribute we're pulling this from, whether it is from a point or a primitive. We can also choose to pull in the value from an attribute, or we could even just set something as a constant value instead. But again, this is how you'll set up the profile for your particular fixture. And like we looked at before, the operator snippets for this operator showcase how those more advanced setups might look and how you could go ahead and add additional channels to the profile and work with those parameters. With the profile for this particular fixture set up, I'm going to head back to the fixture page. And here, just like with the DMX Out CHOP, we can set a net, a subnet, and a universe for this data. We can also set the starting point for our DMX channels with this channel slider. When we're in this auto layout mode, the operator is going to attempt to automatically lay out our channels based on the settings we have here and the starting channel number. We can also add a gap value between the channels that it creates. But I also do want to point out that if need be, you can actually turn this auto layout switch off, and then you can have access to, just like in the DMX Out CHOP, a routing table where you can manually set up that channel layout yourself, and you can specify the primitive within your geometry and the particular net, subnet, universe, channel, net address, etc. that you want to use for that primitive. In our case, we'll leave this on auto layout. My particular device is set up to expect things on universe 1, so I'll adjust that accordingly. I want this to start on channel 1, and I'll leave my channel gap at 0. So as you might have guessed, there is only one place for us to go next, and that is to add a DMX Out POP. So the DMX Out POP takes data from one or more fixture pops, like this one over here, merges all the universes together and sends that data out to your devices using whatever hardware device or protocol you have specified. So we'll see some parameters that are familiar from the DMX Out CHOP, but we also have some new ones as well. So like the DMX Out CHOP, we can choose the interface. And again, we have the option for a directly connected hardware interface or use something like ArtNet or SACN. We have a network page that looks pretty familiar. But then we have a new fixtures page where we can specify multiple fixtures. So we do have the ability to directly connect the fixtures to our DMX Out POP, but we can also specify our fixtures via these parameters here, like so. Like if I want to drag my DMX Fixture POP onto this DMX Fixture POPs parameter, and then depending on our setup, we can add more fixtures, reference the fixture pops for those particular fixtures, and then that will give us a unified place where we can turn on and off the output of the data from those fixtures. So it's a great kind of control hub, especially as you're testing and setting up the fixtures in your space to be able to quickly toggle on and off the data being sent. So I'm going to set this up for my particular scenario. I've got my one fixture pop. On the DMX page, I'm going to send this using the SACN interface, and then on my network page, I need to make some changes here as well. I don't want to multicast. I'm going to set the specific IP address that my WLED instance is currently using, which is 1.188. As soon as I entered in the network address, I'll try to hold this up and see if you can see that. My little LED matrix is now correctly receiving that data and animating just like the texture that I see in TouchDesigner. Before we close out, I do want to showcase one more operator, which comes docked to the DMX Out POP, but also is accessible via the OpCreate dialog, and that is called the DMX Map DAT. This is a really handy operator, which lets you visualize the current data being output, and it'll be deactivated by default because it takes up some processing power. So when I turn the active switch on here, I can actually see in this table all of the different channels of DMX data that I'm currently sending out, and I can get really any kind of information that I need about those so I can really understand what is happening and what's actually being sent from the program to my device. So this is super handy for being able to troubleshoot and understand the setup and layout of your DMX data. So as you can see, this new set of DMX operators really has streamlined and enhanced TouchDesigner's ability to deal with DMX data. Not only can we manage much more complex setups with a wide variety of fixtures, we can also keep our projects more organized and have a better understanding of what data is being sent and to where. Hopefully this has been a useful first look at these operators, and no doubt they'll become a core part of your setup if you're working with DMX Lighting. With that, we're going to close out the video. Thanks so much for watching. Looking forward to seeing you in the next video.
Hey folks, thanks for watching. If you like our YouTube content, I highly recommend you check out the Interactive and Immersive HQ Pro. The HQ Pro is the only comprehensive educational resource and community for immersive design, TouchDesigner, and creative tech pros. In the HQ Pro trainings, we cover almost any topic you can think of, and we go way more in depth than we do in our YouTube tutorials. We have a private group where Matthew Reagan, myself, and our other industry veteran and pioneer teachers answer your questions every single day. If that sounds cool, click the link in the description to learn more. And if you enjoyed this video, hit that like button and don't forget to subscribe for more free TouchDesigner and immersive content.